Document camera's not connected. Eileen. What does that mean? Document camera. Is not connected. There it goes. Yeah.
Everyone in my group 10 minutes per lab costing on the president.
I have the sheet and there is no signature there for you. The sign-in sheet. There is no signature. I looked at that and I said, I know that he was here, but you did not sign in. Yes.
Was I supposed to sign it before we left? I thought we didn't email you, so we didn't do the class.
Okay, well then there was nothing there, so that's my fault then. You just tell me. Yeah, stuff happens.
No, I must sign it.
Well, no. If you emailed me, you probably gave me the list of everybody else. Put yourself in the list. Put yourself in the list, and then what I do is I fill in email for each of the signatures that you gave me on the list. So you sent me the email, but you didn't put yourself in the list.
I guess
that was the problem. Okay, it's nothing to worry about. Okay, it's easy fix. Easy fix. Okay, so then something is hiding here. Okay, I guess it's about time, isn't it? Yes, 1 o'clock. Okay. Remember that we are moving the lecture ahead 1 week. So you have, actually there's 3 quizzes available for you online right now. 1 for today, 1 for last Friday morning, and 1 for last Friday afternoon. And they're all due, I mean, the one that we're talking about for today is not due until the end of September. Okay, so it's not one of those things you have to panic about having it done back then. Okay. All right. We're talking about color systems today. Now, this is a little bit of a difficult thing to understand because you've grown up in a world in which you just took color for granted, and we can't do that anymore because, as you can see from the machines that we talked about this morning and we used this morning, color doesn't come out the same way. So here's kind of what has happened over the years. Human beings knew virtually nothing about color for most of our history. We knew that it existed. Eventually, of course, Isaac Newton figured out that white light is made up of the primary colors of the spectrum. I showed you that last week. But there was really not much of a need for anybody to figure out how color actually works until pretty much the invention of the automobile and as well as the invention of electricity. And what kind of happened is twofold. In one case, with regards to electricity, what the invention of electricity did is allow people to be able to continue working into the night. Now, to give you an example, yesterday I had a power failure at my house. I was working on a document, and the power went out. So of course, what I was working on my computer was gone. Fine, we would expect that. But at the same time, do you know how little there is to do at 8 o'clock at night if all you got is a flashlight? Have you ever been through that? We've been through that with the hurricanes and stuff like that. But anyway, if you have power, you're able to go outside at night and do stuff, right? And one of the first things that they started doing was playing baseball at night with lights, right? And so the research question was, how much light do you need to have in a stadium? Okay, so that was where we started learning more about how color works. Is how much light do you actually need in a stadium? Then future questions were, how much light does a car need to have? because as they were starting to have cars move around on the roads at night back in the 1910s and 20s, they had to see where they're going, right? So how much light do you need? So there was an organization created to study those things, and they were based in France, and I think I mentioned their acronym to you before, which is CIE. Okay, and that CIE stands for Commission Internationale d'Éclairage. Now, I don't know if you know anything about French. I don't know anything about French. I've learned how to pronounce that though, and it's kind of like if you're making a contraction in Spanish, you leave out de. So it's CIE because éclairage is light in French, and déclarage is of light. All right, so this is the International Commission of Light. Okay, and what they did since about the 1930s, they have done an awful lot of studies at CIE about how color and light works, because you know light and color are basically the same thing. Light is made of color. So we need to have some sort of a system to answer questions like how much light, and that's where they started. And eventually they got to the point where they were talking about, well, what color is that light? And well, how do we know how to describe light? How do we know how to describe color? Now, one of the things that would be very difficult to explain is if you would look at the grayish, bluish walls, whatever they are, try to describe what that color is. And, you know, you don't have words, do you? I mean, it's very difficult to describe what that color is. And I'll tell you what, I bet you see something different than the person next to you. Because there are certain things that are about your body, about the physiology of your body, that means that you see things differently than perhaps others. So we have to have some way of talking about color, and in order to make it accurate. And it started back with the CIE. All right, now what you see up on the screen here is called the CIE color space. The image that you have up on the screen is from that color guiding glossary that I suggested that you download and print. It's on the website, again, linked today. This is the actual printed book. They have given me the option to share the PDF with you. And it's on page 15, I think. Yeah, this is the document. All right. Now, you kind of need to know where this is all coming from, because it's part and parcel of what we do today. So this image that you see up on the screen it represents, that's the important word, it represents every color that a human observer can see. Okay? So it deals with the colors that we can actually see. And so let's go on and talk about what that means, because it's a kind of an important notion. First of all, I said it represents, didn't I? And when I'm saying represents, I mean that this is not all the colors that you can see. I think you can probably already guess that the colors that you see up there on the screen are not the same ones that I'm seeing on this monitor, which wouldn't be the same ones that I see on my Mac monitor, which I have sitting up here as well. In addition, what you see here is a two-dimensional representation of the color space. Now let's talk about the word space, because I've already said that before. Space is a volume, isn't it? It's not an area. What you see there is an area. When I say color space is a volume. Okay? So what does that mean about this illustration? Again, it represents, right? It represents the colors that a standard observer can see. So let's go on and talk about what I mean by space then. What we're saying is that within regards of this thing, the space, I don't think that she's seeing the whole thing, is she? They've got it, they're not, it's not set up right. Because you're seeing this, but she's not, right? I don't know. I don't know what I can do. I just, they worked hours on it, and it's a, well, whatever. So the idea is that that's two-dimensional. If you see a two-dimensional thing, we know there's a third dimension to it because it's space, right? And so you see that point right there where the white is? Okay? Up here, this point is black. Okay? So again, this thing represents the space that you can see, but it represents it in two dimensions, and there's a third dimension which comes from this point outward. Okay? So if you look on the walls in the lab, you will see that there is a representation of this color space, as well as another one that has layers of color stacked on each other. Okay, and that when the layers are stacked on each other, kind of give you an idea of the depth. It's kind of like if you were to look at a map of the globe on paper, on flat, it is not the same as looking at it as a globe, right? Because the globe gives you the third dimension. In this case, the third dimension is a vertical axis that comes out of the other. All right, so far you understand that this is a representation that deals specifically with the two dimensions of the color, whereas the darkness level is the third dimension that emanates or is up here somewhere. All right, so in other words, if I have a point up here, then to every point, you see, to every point, there is an axis, isn't there? All right, there is a line connecting this black point, which is nothing, right? No color. And to every point, there is an axis that goes there. And as it gets here, it's lighter, darker, 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 black. Okay, good? So we talked about the representation. The second thing that I said is that it is of a standard human observer. Okay? So the first tests that they did along these lines, they used one man, and it happened to be a white English man. Okay? Now, those of us that have heritage from places that are white with snow and ice have a different visual acuity than those who are from more verdant, who have a heritage from a more verdant place. So, as time went by, they added to the measurements not only this white English male, but also people from every ethnicity and both men and women. So there are basically hundreds of people, maybe thousands, that have been measured over the years in order to find out what this standard observer is. Okay? Are you real clear about that notion? So in other words, this is what humans can see, not necessarily every human. Okay? Good? Now, the way that we're going to be starting to think about color is based upon some sort of measurement. All right, so this is the big daddy of all this, and we're going to talk a little bit about a couple of other things and then come back to this a little bit more. All right, so when we talk about the systems of measurement, okay, this is the granddaddy from which everything else flows. But there are other systems as well to define things. So how do we define? You defined this morning a brown as, what was it, 40, 20, 40, something like that, whatever it was. You defined that in CMYK, didn't you? All right. So is that a way of defining color? Sure. It is a way of measuring color. You put numbers in there, didn't you? And you therefore can measure what you entered. On the other hand, you also used a device that measured the spectrum, didn't you? Right? So the first system that I want to show you that is a measurement system. All right, so we're talking about color measurement systems. We'll go to Photoshop. And go to the color picker. And hopefully you can all see that, okay? There are several systems in here, all right? You see HSB, RGB, CMYK, LAB, libraries. We use that today in design because we picked out the Pantone library and the Toyo library, okay? And right down here, there's also hexadecimal. So what this is saying, this device, this color picker, allows us to describe colors using several different numeric systems. And again, those are HSB, RGB, hexadecimal, LAB, and CMYK. So those are the measurement systems. So let's talk about what HSB is first, okay? Now, if we look at what H, S, and B are, they're all set to 0 now, right? So there's no hue, there's no saturation, and there's no brightness, okay? So let us take the saturation and put it to 100% and the brightness to 100%, and you'll see that 0 hue is red, okay? Now, the HSB system is extremely important for people who are artists, okay? So HSB is the way that you're going to think if you are an artist or a painter, a graphic designer. You think in a photographer, you think in these terms of hue, saturation, and brightness. So the H is the hue. The hue is the name of the color. Now you might know that in the email I sent you to bring something today, which thank you. By the way, I've got to tell you, this is the first class in which everybody, all the students, brought something to measure. Thank you very much for that. I appreciate it greatly. All right, so I asked you not to bring something that is charcoal gray or whatever, because I need you to have a color. And I didn't say hue because I hadn't discussed that with you yet. All right, but that's what I wanted. I want something that's a hue. And you brought me orange or blue or green or teal or whatever, okay? So 0 degrees. Where's 0 degrees on the circle? Where's 0 degrees? All right, right there, okay? Or here to you, all right? So my point is that this is a color wheel, all right? So H is on the outside of the color wheel. Now, another way of looking at that, and I'll see if I can figure out how to do this without crashing the whole thing. And I need to do this one, right? Is this my right one? Okay. All right, so if we talk about this, we're talking about R being there, okay? And the color wheel goes all the way around. All right, so it's R, G, B, red, orange, yellow, green, blue, violet, right? Red, orange, yellow, green, blue, violet, and actually indigo over there too. So you have all the way around the circle, okay? Does that kind of make sense to you? All right, so with that drawing, okay, how do I get out of this? Maybe this button over there. Probably that one right there, huh? All right, so what would happen if I added 180 to this? By the way, what's the biggest number you can put in HSB? What does it say? Can you see it right there? That's degrees. So what's the biggest number I can put in there? 360, all right? And 360 is the same as 0, isn't it? Because you go all the way around the circle. All right, so if I'm here at 0, which I guess is, and 180 is over here, can you tell me what color it is? All right, we're going to type in 180. I have to remember I'm using this keyboard, not the Mac. And actually, it's cyan, isn't it? All right. Yeah. Do you follow this, guys? What are 180 degrees apart? What are they? Tell me loud. Complementary colors. Okay. They're opposites, aren't they? And if I am at 0 and at 180, how much more opposite can you be? Are you clear about that? All right. So those are opposites, aren't they? Now, what if I put in 90? There's my green. It's kind of a puke green, but there you go. And if I type in 270, it's the bluish purple color. You see what I'm saying? So where the color falls on the color wheel. Now, is everybody familiar with the color wheel? I had to make one when I was in college, but I don't think I need to have you make one of those. But anyway, you have to go around the circle: red, orange, yellow, green, blue, violet. It's taking the spectrum and putting it around a circle. Okay, good. So I need you to play with this, and we will do a project with this next week. I had you measure a color today, didn't I? There's a reason for that, because we're going to use it for a lot of projects that you're going to do down the line. Okay, if I go 360, what's it going to be? Red again, right? Because it's all the way back to 0. Good? So you understand what the H is. So let's leave that alone and go to S. All right? Now, S is saturation. Today, in class, in the lab, in the morning, I called it dirt. Okay, so to be real accurate, instead of putting, the colors in that order, this is cyan, isn't it? And over here is my green, etc. So we know that the colors actually fall where they are. And you can type every 90 degrees and you find out where everything goes around the circle. But my point is that if you take this color and mix it towards the middle, all right? If you take it and move it towards the center, okay? What are you doing if you take red and add cyan to it? I showed you this morning. You make it dirty, all right? So right in the middle, theoretically, in a world that is perfect, it should be gray. Okay? But what's missing? Blue. Remember, I had a mind fart this morning about that. Right? Maybe that'll help you remember that Wade blew it. All right? So, but we know that it's going to be kind of a brownish color because of the imperfection of the blue. All right, but you see what we're doing is we are now taking, I wonder if I can do this. We're taking this bright color, and instead of being 100% saturated, we make it 50% saturated, and that's halfway across, that's moving across that circle. And if it's 0, if it's 0, it's gray. Okay, that's a gray tone there. Now, again, that's theoretical because we know that pigments are not perfect. You see what I'm getting at? The saturation is adding the other color, the dirt that I showed you this morning. It makes it less bright and exciting. All right? That's saturation. Now, the next thing is remember that these things are color spaces. Okay? Now, when I talk about any color space, it has to have a third dimension to it. Okay? And that is the B. All right? So, again, remember that the horseshoe, there's a black out here, right? And so what that is in the case of HSB is how dark it is. And right there, 0 is black. So if this was a third dimensional thing, out here would be black. All right, so that's 0, and you're getting stronger and stronger and stronger as you get towards the plane. Okay, and every color does this exactly the same way I showed you with the LAB or the CIE demonstration. Okay, so those are the aspects of HSB. So this is very important to understand how this works, and that's why we're going to do projects with it in lab, because this is how graphic designers, photographers, and artists are going to speak to you. They're going to say, well, you know, that red doesn't pop. hell does that mean? How can red pop? Pop is when you have something and you press on it, it goes boom. How can red pop? Have you ever said it doesn't pop or something like that? Yeah. What do they mean? It means it needs higher saturation. And how do I give something higher saturation? You take away the complementary color. You see? They'll talk to you about pop all the time. Or that red doesn't speak to me. Got it? All right. So HSB is the artist's way of thinking about the world, right? Now, if we are dealing with electronic media, RGB. Oh, by the way, what are the values in H, S, and B? There's 0 to 360 for the H, right? For the S and the B, it's 0 to 100. 0 is no saturation for S. 0 is black for B. All right, now, Ken, I don't think that she's seeing the right stuff here, because isn't there supposed to be that in a corner? Well, she can't see what I'm showing on this monitor. She can? Okay, all right.
Using sound. Sound recorded on TV.
Okay, but you know that she's seeing that.
Yeah, the screen.
Okay, because I thought that it showed a small piece of it somewhere. All right, good. So you understand what the numerical descriptions are. All right, let's go to RGB. RGB is all about displays, monitors, and anything it does with digital colors. And the values of R, G, and B are 0 to 255. Okay, why 0 to 255? I'm sorry? 256 total of each color, which goes back to the ancient days of 8-bit bytes. I told you this in 3351, right? So 8-bit bytes means that you could have a word in computer lingo that could be up to 256 different variations. Why is it 0 to 255? Because 0 is one of the 256. Okay? So we have that range from 0 to 255. Now, HSB is pretty easy to understand. I would say artists can do it, so anybody can do it. I won't say that, okay? Come on, lighten up. But RGB is pretty difficult to figure out what the hell it means, okay? So you have to play with it a little bit and add the colors. And right now, red is turned on 100%. I did this for you last week. There's the yellow, right? I did all that stuff for you. So we're going to take your color and we're going to play around with its RGB values as well, so that you get an idea of how the RGB system works. RGB is not intuitive, okay? We've used CMYK a lot, okay? So I'm not going to talk any more about that, but we do have to talk about this LAB, all right? Now, LAB is, like I said a moment ago, the granddaddy, the one that makes everything else work, okay? Now, I need you to kind of follow along with what I'm going to show you here. There are very unusual axes within this. So right now you can see the y-axis, all right, and the x-axis, all right, and these are all measurements of the spectrum. So what I'm showing you here is a way of describing in 2 dimensions that band that is the spectrum, okay? So this is the x-axis and the y-axis, and you don't see x or y anywhere in this description, do you? Okay? You see something called L, something called A, and something called B. LAB. Okay, are you ready? Human beings can see, and that's represented by this and the other axis and the vertical axis. Human beings can see 4 billion colors. The standard observer can observe and discern 4 billion colors. That's a lot. Okay? We mentioned in 3351, we talked about 24-bit color on a computer. All right? If I take 24-bit color, you know that's 16.7 million color, right? We did that math already. You know it. 16.7 million sounds like a lot. How do I get a calculator on that? Right click here?
No, you just get a click that button.
Yeah.
You go to all programs.
It's right
It's right there.
What a lousy calculator. I wonder. Oh, where is it?
It's still on yours.
Yeah. All right. Is there a way to make this thing to? All right. I'll just do it. All right. So I want to take this 16.7 million. All right. 16,700,000. Did I do that right? 16.7 million. Yeah. And I want to divide by 4,000. That's 4,000. 4 million. 4 billion. Did I do that right? Equals. You see that your monitor can show you about 1/2 of 1% of all the colors you can see. You should be thoroughly impressed by that. That these things that we take for granted, monitors, TV sets, whatever, are really massive jokes when it comes to color. And printing is far worse, because we're at about 100,000 colors that we can print. Whoa. There's much more out there than meets the eye. But Dr. Wade, I can use 16-bit color. Yeah, but you do the math there and you're up to 2% of all the colors you can see. All right? We have a big problem there. All right, so tell me a little bit about what you see. And I don't know if I can turn this around. I tried this. I don't know if everybody can see it. It stopped somewhere, didn't it? All right, can you see that what you see on this thing is much better than what you got up there? If you have it up on the screen, you can see it right on the back, so it's better for you to see the actual colors, because that sucks. All right, so if I look at the colors that are actually visible, all right, by human beings, what's the most dominant color? Green. Okay. Most of what we see is green. Now tell me why. Why do you think? Why do you think most of what we see is green? I have a theory. Do you? Being able to tell the difference between a green stick and a green snake is really important to us. All right, because we would not have existed or continue to exist. You know, we human beings have no natural defenses at all. The only thing we have is smarts. And that's part of what we see is so valuable to us. All right, so if you see up there, most of what you can see, as described by the color horseshoe there, is green. All right, now this is important. We have these other axes. All right, right now we've got the y-axis and the x-axis. And you know you can have as many axes as you want, right? There's an axis that goes from here. Can you all see my pointer? Through here. From here to here. What am I showing you? I'm showing you complementary colors, aren't I? Right? And this is my yellow and my blue. Yellow is red and green. See? Halfway between red and green. You see it? All right. And blue is over here on the other side. And you take, those are opposite colors, right? And that is the B, as in boy, axis. Now, how can I remember that? Because B for blue. Okay? So we know that the colors are all organized around opposites, right? So if I look at this axis, I can come from over here, which is blue, to yellow. That's an axis because they are complementary colors. Okay? And it goes from blue to yellow, and that's how, use B. When you think about B, think about blue, right? And banana for yellow works too if you can use that mnemonic, all right? Then you've got here's magenta, all right, and there's green. So that's the a-axis, okay? So the a-axis goes from green to magenta, and the b-axis goes from yellow to blue or blue to yellow, whatever. It doesn't matter which way you say them, okay? Now, both of these axes cross right here. You go across here, and so right here is where those two axes cross, and that's white. Okay, so the A and the B axes cross, and where they cross is white, because it's all, right? White, as we know, is all colors. All right, so now we understand a little bit about the A-axis, and we understand a little bit about the B-axis. All right. Now, I'm about 99% sure of what I'm about to say, but I'm not 100, so I might be wrong. The way, you know what a number line is, right? You got 0 in the middle and negative on one side and positive on the other. Yeah? So that's how these axes work. The 0 number is right in the middle of white. All right, so A0 is in the middle of white. B0 is in the middle of white. Now, going this way is negative, and going this way is negative. So this is positive, and this is positive. This is negative, this is negative. Okay, well, again, we're going to have to play with this a little bit in class to make sure it's right, that I'm telling you the right thing. I'm about 99% sure. Okay, so let's go back to the color picker, and we understand that the A axis, can you see the A is negative 16? So it's to one side. It's not to the lower right, it's to the upper left of white. And B is a positive number, isn't it? So it's the opposite direction. All right, so you can see where that falls. And you go back to over here, and yellow is going to be over here somewhere, isn't it? Right? It's going to be on this side of the A-axis and this side of the blue, or the B-axis. Now, that's confusing as hell, isn't it? So you might ask, well, why do we use this at all? And we'll get to that, all right? So just hold on with me at this point. All right, there's one other axis here, one other measurement, and that's the L. All right? So if we go back to that illustration, we've already mentioned this before, but we go back and do it again. Up here is 0, okay? So all of these colors have an L that goes from 0 to 100. And so every A and B value has an L value as well. It goes up here. The plane of this chart is 100%. All right. Up here is 0. So the L value goes from 0 to 100. Okay. Does that start making sense to you? A little bit. Okay. What is that? That is a representation of what the standard human observer can see. Okay. Now, to give you a frame of reference, and it's not a very well drawn frame of reference, but you see the triangle on that? That is a description or represents what a monitor can show you. Okay? Why? There's a red, a green, and a blue point. Notice that monitors suck when it comes to green. Do you see that? Green is the most important color to human beings, and monitors don't show it to you. Isn't that awful? Right? Now, the hexagon, and that's a word we're going to throw around a lot in this class, the hexagon represents CMYK. Where's K? Which is kind of a funny thing because I call my grandson K, and he's at my house right now, so K is at my house. But anyway, his name is Caleb, so we call him K. Not spelled that way. Where's I have black K? Where is it? It's up here somewhere, isn't it? It's the third dimension. All right. So why does CMYK form a hexagon. What's hexagon mean? It's six-sided, isn't it? Why? Last week. Well, obviously you have cyan, magenta, and yellow, and if you overprint them, you get the red, the green, and the blue, don't you? So that's 6 colors, is it not? Yes? If you overprint them, you get the 6. Okay. Later on this semester, we'll talk about something called G7, which is the standard way now of controlling printed color. G stands for gray. 7 is the hexagon plus the black point up here. All of it fits together, ladies and gentlemen. All right, so you can see that in this, there's my yellow, right? Right here is my magenta. Do you see that it's not a very good solid point? You'll learn more about that later today. All right, here's my my cyan, right? You see my blue, my green, and my red. You see it? Those are the points. I would like to point out to you that printing does a better job of reproducing greens than monitors do. Now, what does it mean to you? That means that you could be looking at an image on a screen that has green content that the monitor cannot show you. But it will print. It's like, whoa. Do you start to see a little bit of complexity going on here? Okay, so you surrender. Oh, no, one more thing. We also had the spectrophotometric curve that we did this morning. And remember that gave us a whole bunch of numbers? All right, there's a whole bunch of numbers. And what were those numbers? Can you remember the definitions of them? Anybody? There's L, A, B, and X, Y, and Z. All right, and X, Y, and Z is another way of describing the same thing. Okay. So you surrender, and you say, I can't possibly understand any of this stuff. If you do, that puts you solidly in the camp of graphic designers and artists, which is fine. So what we're about in technology is about understanding this stuff and using it and exploiting it. Okay, so what often occurs, and I showed you this morning, and I didn't bring it today because I hurt my back and I don't want to carry too much stuff, is a swatch book kind of thing, all right? And this is called a color appearance system. We've been talking about color measurement. How do we measure colors? We use numbers to describe, all right? Measurement is always about numbers. Color appearance systems is this. I'll know it when I see it. I'll know it when I see it. To a technologist, that's something that just drives us out of our minds. I'll know it when I see it. And this morning, what did we do? I said, pick me a color. You pick me a color, right? You'll know it when you see it. Right. Now, this is a different version. And I want you to see this and pass it around. This is not Pantone. You see that it says True Match on it. Now, True Match is an English system. And it is based upon it. You can go to any color. You can flip through any color you want. And you can find the color that you want. But instead of having a set of ingredients like the Pantone book does, it has CMYK values. Okay? It's kind of like the version of the Kelsey was talking about this one. She was talking about the version of Pantone that shows the CMYK number. But this is another system. Just so you know that there's many of these kind of systems around, even though everybody tends to think about those that are Pantone. Then I also showed you this book. Is anybody talked to Gary? Is he still around? I haven't talked to him in a while, but if you can get this book, this is valuable. Here's another color appearance system. Okay? So color appearance systems are those that are you can look at it and see it. Okay? Now, one thing about color appearance systems, and this is something you want to make sure you have written down and circle in and everything. is, number one, color systems, color appearance systems. You've got to actually look at the book, the printed version, not the online version. Now, of course, if you're building a website and you want to use a Pantone color and you convert it, blah, 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 that's fine. But, you know, the problem with online stuff, you have absolutely no control over what happens. Zero. You know, that monitor compared to this one, I have no control over it. Especially when my customer might be on another planet, no, on another continent. You see what I'm saying? So when you are dealing with a color appearance system, you grab the version that is actually printed and point to that. Then you choose the same number in Photoshop or InDesign like I showed you today. Don't go through the colors in Photoshop or InDesign in the libraries and pick one out based upon what it looks like on the monitor. There is no relationship. Now you say, well, wait, why are you not teaching me how to do this? Well, we will get close, but we're not going to get further. All right, so we have color appearance system. Good. Now you have the Pantone system, which is based upon ink. Then here's a couple of systems. If you haven't looked at this, take a look at that. That's every one of those patches has a different CMYK value. All right. So those are our color appearance systems. So always, always, always use the printed version, not the online version. And the second thing is that you should always make sure that the book that you are using is clean and fairly new. Now, as human beings, if I grab this book, I put my finger on the page, right? And when I do, then after a little while, the page discolors, doesn't it? So you have to be real careful about that. Okay, so you want to make sure that they're clean and relatively new. They fade. A Pantone book, a book like you're showing, the True Match, this CMYK color build thing, all of this stuff should be kept in a dark drawer, okay? Inside a drawer, so that it doesn't have much impact with light. If you, well, maybe you don't even know what a video store is. You know what a video store is? We used to rent DVDs and videos. Yeah. I remember there was one right across the freeway here in New Territory where I used to live. And they had a window that faced the southwest. And you could walk into that video store and walk around looking at the videos, and every box, every package, every DVD container that was facing that window was faded to the point where you could only see the black ink on it. Because the light came through and bleached it. Yeah. Now you went on the other side of the same display, and all the printing was just fine. So ink is very susceptible to fading. Okay, so with the exception of black, black is not going to fade, but the colors fade. All right, when we deal with these color appearance systems, there are some systems that are absolute and some that are relative. And this is an important distinction that we're going to have to make more and more as we go through class today. And that is, what is the difference between an absolute system and a relative system? All right. This is the granddaddy of the absolute systems. It's called the Munsell color tree. So in other words, these things that you see up there are actually little patches of color. All right, they are swatches, if you will. All right, and it is in the shape of a tree. Now, it goes around, and what's going around? What's the value going around? H, right? And you'll see that at the top it's white, and at the bottom it's black. So that's your B version, isn't it? Right? And then it goes from outside to inside. And what is that? When it goes, you know, if the outside circumference is the hue, then as they come towards the middle is the saturation, isn't it? All right, so you see that is HSB, isn't it? All right, you kind of follow that? Now, these things have been around a long time, a lot longer than the CIE color space that I showed you. But this was done by trial and error. Those chips remain that way. They stay that way. They're absolute. They don't change. Now, they can be worn out or they can whatever, but the colors that are there remain the same. Okay, you follow that? Now, it'll be easier for you to understand when we get to the notion of the relative systems, all right? Ostwald is another example. This is another way of looking at a color tree. You'll see this is the middle. Okay, this is the stem right here, and that's the grayscale, which is the L value or the B value, if you will. And then it goes out to the color, and you see how the petals work. If you consider what I just showed you, the Munsell system, this is a way of understanding what's on the outside versus what's on the inside. So the outside is the pure color, right? The hue around the outside of the circle. And then you see that it comes towards the middle, and in the middle it gets grayer and grayer, all right? So it desaturates it. And to the bottom it's darker. Those are called tones. And to the up it's called tints, where it gets lighter and lighter, okay? So the Ostwald system is similar to the Munsell. If you were to take every single hue, so you'd have 0 degrees, 1 degree, 2 degrees, 3 degrees, 4, all the way around to 360, you'd have 360 branches, or I don't know how you say it, around this tree, right? And every one of them would be at the outside of the triangle. Towards the middle would be the saturation. Top would be the lighter values, and bottom would be the darker values. All right. And again, those things are painted chips. They're there. They remain the same color unless they're damaged or something. Okay. They are absolute. Okay. They don't change. Now, on the other hand, and this is a very big, important kind of thing. On the other hand, if I am going to print the image, if I'm going to print the image and I use Genie as compared to Marvin, then the colors that are chosen from the book or from that true match or whatever change. Okay? So with the Ostwald and the Munsell system, they're absolute, meaning that they do not change based upon printing, because you're not printing them. They are a reference, if you will. All right, if I take a color and I print it on paper, and you've had experience with this, I can change the color in many ways. One way is that I can run the ink density up by 0.05. That changes the color. Or I can run too much water. Or too little water. I can run the density too low. I can not set the keys across the sheet properly so that some parts are lighter than others. Okay? I can change the substrate. I can change the color of the substrate. We'll talk more about that in another class. But if I have white paper versus eggshell paper versus cream colored paper, the reproduction on the paper the reproduction of the image on that paper changes. You see how those images from the book or from True Match are relative. And what are they relative to? The substrate, the machine, and the ink. All right. So there's a lot of variables in those systems. So bottom line is that you can have a color that looks perfect in a book like a Pantone book or the Ostwald, not True Match, but appear different when it's printed. You also know another little thing that impacts this a lot too. which is that little variable called dot gain, okay, or tonal value increase. If you don't set all this kind of stuff right, those appearance systems are pie in the sky. There's something that is whoa, that would be nice. Like sometimes the Jews say next year in Jerusalem. All of a sudden, next year maybe we'll get it right. It's one of those things that is very difficult to deal with. All right, so you got the idea. The relative systems are all based upon something. Now, there's a whole bunch of these systems out there, and we looked at some of them today. But if we go into the Photoshop, for example, and do our color libraries, okay, you can see just a few of them. All right, there's a whole bunch, right? ANPA, American National, where is it? ANPA? American Newspaper Association. American Newspaper Association. So they have their own sets of colors, right? If I click on that and choose it, then they have a series of colors, not very many, but they have a series of colors that are specifically for newspapers. And then DIC is Dynapon Ink Corporation. Dynapon obviously sounds what it is, it's a Japanese ink manufacturer. All right, Focal Tone. Focal Tone is an English system. You go to Focal Tone, and it has certain numbers and colors, and you know it looks like a Pantone book, doesn't it? All right, so there are all these different versions. Then let's talk very briefly about HKS, because we're going to come back and talk a little bit more about this. HKS is hexadecimal, or I'm sorry, hexachrome. And it's about using not CMYK. CMYK is 4, isn't it? But hexachrome uses 6 colors of ink. And I'll just give you some examples later on in the semester. It uses CMYK, orange, and green. And it is an incredible difference in what the final reproduction looks like. All right, so there's a whole bunch of different HKS systems. And then you have, look at all these Pantone things we talked about them this morning. I showed you all the massive number of books there are and all those. And here's our Toyo, right? And there's True Match that I just showed you today. All right, so you see there's a bunch of different libraries, and all of these things are color appearance systems. And this is how you would choose in Photoshop one of these colors. You choose the color that you want to use and go with it, right? But you don't pick it from here. You pick it from the printed book. You pick the True Match color from the printed book. Is the printed book perfect? No. Because I on the press over there, I can change the color just by sneezing on the press. I know you all hated shots. Did anybody like shots? If you like shots, there's a competition every year, student competition. If you like shots, I would like to enter you. But shots allows you to do all sorts of damaging things without actually damaging anything. And one of the things that you can do is increase the ink density and see what it does to the color. I mean, this is an incredible tool that you've played with a little bit, but I know you all hate it. All right. So we've talked about HSB. I think that I've covered everything that we need to do with that. We talked about CMYK. And now let's go into talking more about the LAB stuff. All right. If you look at my teaching notes, I think I've hit most of these points already, but I do want to go into much more discussion of LAB. All right. One of the important things that you have to understand is that there are these systems that are absolute and systems that are variable or can be changed. And the big point, the big takeaway for all of this stuff is about, well, if I am going to reproduce a color, that color is. The color exists. We know that the color that we see is dependent upon the light source and the item itself. So what's the item doing? The item is absorbing and the item is reflecting. Yeah. We know that. But that item actually has a color if it's being properly illuminated. So that color, that thing actually does absorb part of the spectrum, doesn't it? And it reflects part of the spectrum. Okay, you with me? Now, I know, and I think we made a mistake the first day that we worked on color, and we changed from one sRGB to RGB. Remember, and all the RGB numbers changed? Is that absolute or dependent? Is that independent or dependent? Okay, listen. We had colors in RGB. We changed from one setting in Photoshop to another, and all the colors changed. Is RGB a variable, or is it a long-lasting absolute system? If it was absolute, then it wouldn't have changed.
That's what I'm saying. Why would it change to certain numbers if it didn't?
Because your monitor was different than mine. Yeah? See, in other words, it's a variable. When I have a color on the monitor, even a PC, I can go in here somewhere and I can change the color balance. I can calibrate this monitor. I can characterize it, right? And it changes what I see. Now, if you guys are into web or videography or anything like that, you have to understand that it's a killer. It destroys the color as you send it out to another monitor because there's no control over the other person's monitor. None. At least in print, I can control stuff because I'm in charge. But when somebody else receives it by a computer, it's a problem. All right, so we need to understand that the devices that we use are variable. They're not absolute. All right? The press, the amount of humidity in the air, the smog, the settings of the rollers, the amount of pressure, the paper, the absorbency of the paper, the smoothness of the paper, the coating of the paper, the kind of coating of the paper, the color of the paper, all change everything. Okay? So if I have a color X and I put it on a monitor that's calibrated, I get a certain color. If I put it on another monitor that's not calibrated, I get a different color, right? If I put it on an inkjet machine with crappy paper, I get a certain color. If I put the same thing onto an inkjet printer with good coated paper, like photo paper, I get a good or a different image. Bottom line, I shouldn't have said good. I should say different, because all of these images are different, aren't they? All right, so all of them are dependent. Okay, all of them are dependent. And what are they dependent upon? The device. You already said some of them, Meg. You said the press, the ink, the substrate, all that for print, but for computing, even more so, because every monitor is different and every color card is different. The color card is where you plug the monitor in on the computer. PCs in particular, bless you, have a tremendous variability when it comes to the hardware inside the box, because you can really put anything you want. Whereas Macs are a little less variable, but from the low end to the high end, there's different technology in them. But you see what I'm saying is that all of these things are dependent, okay, upon device, etc. So how in the hell are we going to try to make this one on this paper the same as that monitor? That's what we want, isn't it? We want my daughter-in-law, who bought her wedding or what they call bridesmaids outfits online. We want her to be able to see the color the thing is. We want Eileen's shoe to be the right color that it actually is, right? We want it to be the right color on your phone, on an iPad, on the screen of a monitor, on a television set, and a printed version on cheap paper and good paper. We want it to be the same color. We don't want much to it. All right, so how do we go about making that happen? And the way that I don't have enough space here. This is so difficult to work in this room. As you see, I've taken up the whole front row, and I still don't have enough space. All right, fine. Come on. Okay, now if we accept the notion that there is such a thing as a color, it is a color. If we accept that notion that this thing, this object, this swatch, whatever it is, if we accept the notion that it is a color, we know that there are some things that it is dependent upon. The color is dependent upon what it receives. Okay? So if you give it the wrong light source, all bets are off. But if you give it D50 light, it is a certain color. And what does it do? What does this spot do? Some of it absorbs, and some of it gives it off, right? Okay? It reflects, if you will. All right. The way that we can solve some of this in terms of making the color more consistent across things is we say, well, if this color is, if it is this color, then we're going to define this in L asterisk A asterisk B. And that's the proper way to write it, not LAB. They left the asterisks out when they put it in Photoshop and InDesign because it took up space, I guess. All right, it is a color in LAB, which means, and remember, every color a human being can see is represented in LAB. Okay, so there is somewhere where it's going, where that color is. Okay. Back to every color, everything, every object is on there or somewhere between the white point and up here. Okay? Every color is there. So if we have that coordinate, if we know where it is in terms of the A, the B, and the L, okay? If we know where it is, then what we can do is go back and forth and say, okay, if I have this color, what I can do is I can take it over here and I can put it on paper. We're using a flexo press, using cheap paper, whatever. All right, I'm just going to make some description, sorry. And we can take it over here and we can put it on a Dell monitor. And we can take it over here and put it onto a, let's say a 4K TV. And we put it over here and we put it on, I don't know if you can actually see what I'm drawing here. And over here we put it on an iPad. All right, so my point is if we know what the color actually is, then we can transform that color to meet the needs of the output device. All right, to meet the needs of the output device. Now, you're not going to be able to get all of the colors because, as I showed you, there's more greens in CMYK than there is in RGB. Okay? But you can get it darned close. And that's, this whole process is called color management. And I think I've given you a little history lesson on that, in that what happened is, remember the CIE, that's the light group, right? Eclairage is light. France, blah, blah, blah. All right, we've done that. We also talked about ICC, right? And that's the International Color Consortium. And we talked about that. I'm pretty sure we have. And what happened is Apple and Kodak and Microsoft and AGFA and all the companies that have anything whatsoever to do with color all got together and came up with this ICC, International Color Consortium, and they came up with a process that on the Mac is called Color Sync, and on the PC is called Kodak ICC. So there's no difference in the technology. It's just called different things. Apple always names its things whatever it wants. So Color Sync, and this is about the early 1990s. This technology came out. All right. So what it does, and you've had a little experience with this already. All right. Let's talk about what happens. What you already know. You took an IT8. Yep. And you scanned it. And then you had software measure. And my question to you, because we didn't talk about this before, I just told you it was like a magic box, right? It's a genie. This software measures in LAB. Okay, so it measured each of those spots, each of those swatches, and there were hundreds of them, right? It measured them all in LAB. How did it do that? Well, in essence, what did you do today? You use a spectrophotometer to see what in the world the spectrum actually is being reflected off an item, right? So that's what the system does, is it looks at it from the spectrum and then puts it where it's going to be on the, I don't have the horseshoe up there now, but it puts it where it belongs on the horseshoe, okay? So it measures what was scanned. So the scan measures the scan, or the software measures the scan in LAB, all right? Then what happened? You remember what happened next? The software compares to a reference sample, to a reference table. Remember we had to choose that when we set up the scanner? You had to choose what reference file you're going to use. All right, and it goes back to when that IT8 was made. When the IT8 was made, somebody measured it with a spectrophotometer and recorded all those numbers. So now, what came out of this whole system? What was the outcome of all that? What came out of all that? Come on. Come on, profile. Okay? So, let's talk a little bit about how you can take absolute and relative and put them together. By the way, ICC and LA and CIE talk about independent, which would be the absolute, right? And dependent. Okay? So what's the absolute value of any color? The absolute value of any color is what? It's what? RGB? No. It's LAB. That's where it actually is in comparison to what a human being can see. Now, I'm sorry, we don't care what dogs see. All right? We care about what humans see, because we're not selling print to dogs. We're not selling websites to dogs. We're selling it to people. All right, so that's what matters. I love dogs, but we don't care what they see. All right, so LAB is the absolute, right? And when it comes to this whole process. Okay, listen and try to write this down carefully. Let's say I've got an image that I had from a camera, a digital camera, okay? When it comes into my computer, what is it in? What color space is it in? sRGB. Okay? As it comes into my machine, my computer, what happens is it is transformed by the operating system behind your back without any permission from you. Okay? It's transformed into LAB. So the computers, I don't care whether PCs, because PCs use Kodak ICC and Macs use ColorSync, same technology. All right, this image comes into the computer and the computer thinks about it in LAB. So the computer thinks in LAB. Now it'll show you RGB values, right? But now let's go back to what happened when I screwed up, what was it, a week or so ago. Remember that I had my settings done to a particular number and your color settings were different, right? And then when I converted, or when I looked at the RGB numbers, or CMYK numbers, they were different, right, than yours. All right, then when you changed, they got different more. All right, so in the background, your computer knows what this freaking color is, all right, in LAB, because as it comes in, it is converted through the profile, okay, into LAB. And then to display it, or to output it, all right, to output, then it has to go through the profile. All right, now the profile is created on your monitor when you do the I1, okay? So as it displays on your monitor, it uses that profile. And so it can output this thing to a monitor. And when we talk about a monitor, we need to know it is, remember the 3 C's? What were they? All right, calibrate, characterize, and convert. Now, we've talked about these things before. What am I talking about today with you here? Okay, we've got an image that has RGB, sRGB. It comes into my computer without anybody's permission starts thinking about this image in LAB. Okay? Then when it's time to output it, when do I output it? All right, remember the computer is over here, okay? That's not the computer. So the image is here. This image that I'm showing you up here is being considered here, okay? It's being thought of here. The monitor, this monitor, that monitor is all output, isn't it? You have to stop thinking about your monitor is what is. Your monitor is reproducing something that your computer has in it based upon the settings you've done for that monitor. So the monitor, you could also set this to be, instead of a monitor, it could be to Wiley. It could be not to Wiley, but to Genie, whatever. I can output in several different cases. Now, in reality, what happens, and most of the time, is we have this monitor, and then from that point, it goes through another profile to output to a device, like a printer or whatever. And that printer could be looking at designing or emulating another printer. And so this printer has to depend upon that one. What is this device here? Kelsey, what is it? If this is my final printer, what's this printer? This is my monitor, this is a printer, and this is another printer. And there's got to be a two-way interaction between these two printers. What is this one? It's the proofer. Okay, because the proof is supposed to be predicting this, isn't it? All right. So you just see what conversion is going on. You're taking a color that is something. All right. We know that it's dependent on the light source, so we give it D50. What it reflects back out is a color. We know what that is. We think about that, or the computers think about that in this absolute system, in this independent system that is called LAB. It's over here somewhere. All right. It's confusing for us to think about because it doesn't have any terms we understand. L, what does L mean? Lightness, right? A, really? B, what is it? All right. You can understand RGB. It's not as easy to understand as CMYK. CMYK, you've been doing your whole life. You didn't call it magenta. You called it red when you were using Play-Doh, but you've been doing your whole life. But this color up here, this LAB, is very foreign. But every color exists in LAB. Every color does not exist on this monitor. Every color does not exist on this monitor. Every color does not exist on that monitor or on Wiley or on Genie or on any other output device. You see what I'm saying? And so the absolute color is where you always come back to. And that is LAB. Okay? Let me give you an example of what we're up against. Oh, that's just really lovely. That's not in my file. Maybe. That's not in my file. PCs. Bad news bears. Can I save? What does save link to Pocket mean? Save what? Save link as? Okay, where's it going to go? I'll just put it on the desktop. Save. PC. Ah! All right, now this, I got all this other stuff here too. I don't need that anymore. Theoretical.
Does your laptop
Not good.
So I have a question.
Yeah.
About how, like, for the sRGB, like, photograph, like, how does the computer, like, think in LAB basically? If it's something that humans perceive.
Because there's this profile. As it's coming in, all the colors are then determined to be what they are actually in LAB. And in the background, the computer's thinking about this in LAB. And in order to show it to you, because you can't show an image in LAB, you have to show it in RGB on a monitor, and you have to put it output in CMYK on an output device. So it has to be converting. So there's all of this conversion going on constantly from one system to another. But the important part to understand is that that image resides in the brain of your operating system in LAB. Yeah.
LAB is more consistent code, so to speak. But why is it that it's not utilized more for branding standards? Just because it's hard for people to wrap their head around.
You can't wrap your head around it. It's a very, if you think about it, it's where on this number line is that color in relationship to these weird axes on something that nobody understands. You can show people this, and they can. I think that you're starting to understand perhaps how it might work. But if I give you a number of -72 on an L scale, what in the hell does it mean? Right? That's a hard thing. Now, it would be a good thing to do, and you really should do this, is that once a color is chosen, then you go into Photoshop and you find out what its LAB value is, and then record that. All right, then that would be the best thing. All right, I'm looking for, this is theoretical. Okay, this one works. So now I need to upload this. I'm sorry about this. This is an important image to look at, though, because I need you to understand what we're up against when we're talking about dependency. Okay, dependency is a huge thing. I need to log on to the server. Okay, it can't find the server. Yes. Is it? Does it work there? Okay. Yeah. That'll be easier for me to do. All right. Let's go to the. Yeah, those are just examples, aren't they? There's a bunch of these pictures in here for you too. Yeah, all right, this makes it work. All right, now we need to understand that we are faced with tremendous limitations when it comes to color. And these limitations are not because anybody's stupid or because we have failed to properly research. What these are is because of the limitations of what we have to work with. There's a difference between theory and practice. And a lot of things are very theoretically accurate and possible. Like making gray out of equal amounts of cyan, magenta, and yellow. Okay? That's not going to work. If I use equal amounts of cyan, magenta, and yellow, I don't get gray. I get brown. Okay? Here's just a problem. All right, now let's take a look at this image. It's up here. What should cyan do? All right, you see in this top image A that red, green, and blue light are all coming equally from the light source. Now that's a big assumption, but assume it's D50 lighting. It should absorb all the red and reflect all the blue and the green. Okay. Now, if you look at what this particular, and this is the important thing we were talking about this morning, this particular ink set, whatever it is, reflects more blue than green. You see the dotted lines there reflect the missing color. Okay? Why? Because it is not theoretic, or it's not practically possible to make a perfect cyan ink, especially at a usable price point. Okay? So you see what's going on there is that it's missing blue. Now, as you saw this morning, most of the colors that you measured also have some dirt in it. And this is not being shown real well here, but I will have you work on a little project in class in which you'll measure cyan ink, and you'll see exactly what is going on with it. All right, so if you take a look at it there, we're missing blue, aren't we? And we're missing green. Now, if I move on, the next color is magenta. And what should magenta do? Magenta should reflect all the blue it receives and all the red and absorb all the green. Now, up here also, this doesn't really show you well enough that this is not all the light that was received. Every paper absorbs some. We call it density, don't we? Right? And really good white paper might have a density of 0.05, which means it is is absorbing some of the light. All right, so we have these two here, what it should be doing, and is nowhere near as much, right? Now we go down to the magenta, and we should. Okay. So the magenta should reflect all the red and the blue and absorb all the green. But in essence, what it does is you see it reflects very little blue, but more red. Okay, so now let's take a look at if we were to stack these on top of each other. All right, we got just some green, right? And we have some blue, but now look at how much behind the blue is getting between this and this. If I were to stack this one on top of this one, all right. Then we go to the yellow. Now we do a very good job of making yellow. We have flowers. We have various minerals to make yellow ink. We do a very good job, and you'll see that when you measure it with a spectrophotometer. Notice what the yellow is supposed to do is supposed to absorb all the blue and reflect all the green and all the red. Now notice what it does is it reflects almost all the green and realistically almost all the red. You see? So the yellow is a very good color, isn't it? So if you stack together those colors, right? If you were to stack together the arrows, the blue arrows all the way down, the green arrows all the way down, and the red arrows all the way down, which is the longest line? The red. Our inks reproduce red very well. Which is the second longest line? Green. Because green is missing here, right? But it's got a lot here. Okay? And then the blue is the shortest line, isn't it? All right, it goes back over and over and over again. You might remember I showed you pictures of the spectrum photometric curves of paper last week. I can go back and find them again if you need to. But the idea was that paper is missing blue, right? Because paper is made out of trees. I mean, trees are brown. And so there's just not enough blue in there to make him. If wood had the same amount of blue as yellow, the tree would be gray. Okay? It wouldn't be very attractive. But you see, it's not neutral. It's brown, right? So when we have a paper that is missing blue, and we have the ink structure that is missing blue, then everything that we do is missing blue. Okay? That's a very, very, very important concept that you have to get into your head. I'm not sure if there are any images that I can find on this because I've never opened anything here. How can I do this? I can open. Where can I go to the computer? This is Homes. This is Vision. Yeah. Let's see if I can find something. 4373. Care pack. And test targets. And where is the right one? I want to open a color image for you here. And I know it's here somewhere. I just wasn't paying enough attention to it to set it up earlier. There is an image. Maybe it's easier to find there. I used it for you in other classes. Yeah, the one with the women in it. I thought it was in the Care Pack Houston. Yeah, I've showed it to you before, but I just want to show it to you again because it's a very good, solid image. I know it's here somewhere. RGB color spaces, test targets and images. It should be under test targets and images. Ah, think this is what P P7 control bar. The IT7 is the IT package. Yeah, if this was my own computer, I'd have all sorts of things here that I've used in the past on the computer, but I don't have anything here. I know that there's some images that are appropriate, but if you were to take a color image, I wonder if there's any pictures on this machine. NVIDIA. This is crap. Oh, sample pictures. How about this? Yeah, we probably could use this. All right. How can I open this in Photoshop? Can I right-click it? Open as preview. Open with. I don't want Illustrator.
I can just put open.
Yeah, just close that log.
Oh, yeah.
Yeah, but it's going to open it in some kind of a browser. Oh, okay. All right. All right. So let me show you. Right now, this is in RGB. All right. So I'm going to add a convert to profile, and I want to Grackle. See, we don't have Grackle on here, do we? Oh, there it is. Ooh, look at that. Cool. Okay. All right, so we have a CMYK image. So if I go to my channels and I look in these deep blacks around here, if I am building this image out of, and we need to do this in lab so you can have a better idea of it. But if I build the image out of CMY, can you see that all of these colors are supposed to be black, and they're kind of a brownish. Again, this monitor is crap, all right? But if you look at it here, as you build the colors, you see all that stuff is brown, all right? Why? Because everything is designed around the fact that we're missing blue, okay? So how does CMYK fix it? It really is bad in the shadows. If you look at that image really massively sucks. You put the black on, and the black covers it. It's the key to making it work because it covers the lousy brown. We have problems with blue, and that's one of the most important things you're going to have to learn about color, because there's always going to be problems with blue. Blue missing from paper, and the blue missing from the ink sets. Okay, I want to make sure that I've covered everything, and then let you go on your way. We're almost done. A continuum. Why would you call LAB an opponent system? Why would you call LAB an opponent system? Why would you call LAB an opponent system? If something is a positive number on one axis and it's a negative, it can't be the opposite. All right. Opponent means opposites, right? And so what you've got is these opposite ends. It's like a number. If it is one color, it's not the other. Okay. So a term that we use sometimes is complementary color. Complementary and opponent, in essence, mean the same thing. Complementary is a nicer word to say, perhaps, but if they're still opposite. Complementary, two things make a yin and a yang make the whole, right? Opposites, right? LAB is an opponent system because if it's on one end of the scale, it's not on the other. If it's on the yellow end of the scale, it's not in the blue end. All right? Makes sense? So that's an opponent system. Okay, why don't I, because we got a couple of minutes, let's go to the actual quiz for this, and let's see if there's any, we can go over some of the questions. Come on. Well, I guess I might as well, no, I shouldn't show it to you. That's dumb. Oh, well, testing quizzes, here we go. So this is for quiz 4. Okay. What's the most commonly used color appearance system in the United States? Color appearance. Appearance is what it looks like, not how it measures. Pantone. All right, can you tell me some names of color measurement systems? We've talked about several of them. Color measurement, RGB, CMYK, HSB, and LED. Right? Those are methods of measurement. And the spectrophotometer is also a system or a measurement tool. The spectrum is it. All right, what's the L channel? Lightness, okay? And the A channel is a continuum. Continuum is another good way to say it. In other words, it's like a number line. Is a continuum, A channel between what and what? Green and magenta. Or magenta and green, either way. Doesn't make any difference. And let's talk about the B channel. Is the continuum between blue and yellow. Always remember, so long as you remember the B is blue, the rest of it falls in line. Because you've got opponents, right? Blue and yellow are opponents, magenta and green are opponents. And you get everything involved there. Okay, I already asked, why is it referred to as an opponent system? An opponent system means that if it's on one end of the scale, it's opposite. Opponent is opposite. Doesn't mean you don't like somebody. It means it's the opposite. All right. What's the difference between color measurement systems and color appearance systems? What's the difference between color measurement systems and color appearance systems? Color appearance is what they look like, and color measurement systems is what they measure. Okay, good. Okay, Munsell. All right, Munsell is a color appearance system, isn't it? And it's an absolute color appearance system because it's not dependent upon ink and paper and all that kind of stuff, or phosphors on a monitor. The Munsell system is similar to which color measurement system? So the Munsell is an appearance system, but what system of measurement is it similar to? Munsell and Ostwald are both appearance. Okay, Munsell is appearance. What measurement system is it like? HSB. Yeah. Okay, I think that was. Not yet. Look at that, it's working now. I have, isn't that mean I'm using, oh yeah, it's from a different page. All right. All right, so that's, you see that? That's the Munsell. And the H is around, the S is across, and the B is top to bottom. Okay? So you see how it relates? Oh, here's something I didn't cover very well. We've talked about color space. Okay, color space. Another way of saying color space is color gamut. G-A-M-U-T. Can you define gamut in a sentence?
It's Photoshop. It's goes up on your screen and print it.
The students in digital media run the gamut from 17 years old to 75 years old. All right, so it's a range, isn't it? All right, and a space is a range also. So you see what I mean by gamut is kind of a range. So we have color gamuts, which are in essence another way of saying color space. Yeah, okay? The amount of color that you could see is a color gamut or a color space. The bigger the space, the more colors, right? The smaller the space, the fewer colors. Space and gamut are sort of used similarly. All right, so tell me which of these is the biggest gamut. Now, we haven't talked about it yet, but think it through. which is the biggest gamut? And RGB monitor or LAB? Which is bigger? LAB. LAB is what the standard human observer can see. All right, that's it. Okay, that's the big picture. All right, so that's bigger, right? Now, which is bigger, CMYK or RGB? RGB is bigger. Okay. Now, when we get to CMYK, as you know very well, is very dependent upon the paper, right? All of those are the same color. I showed you a blue one this morning. Which has the bigger gamut? A CMYK on newsprint or an uncoated paper? Uncoated newsprint is worse. Okay. Why? Because there's not as much of a white area, right? The paper itself is brown. Haven't bleached at all. All right, which is bigger, the gamut or the color space of CMYK on uncoated paper or coated paper? Coated is bigger. All right, so you can see that the gamut or the space, the range, the spectrum, or not spectrum, I shouldn't say that, of colors is variable. All right, so that's one of the questions. This question is sort of based upon the picture I showed you last week. Let's go and crap. Okay, now this is a pretty important question. Hoping I didn't ask it to you twice, but if we go back to week 3, we did that. Okay, what visual impact do the specific wavelengths of light emitted by a light source have on an object? What visual impact do the specific wavelengths, and you're looking at them right there, of light emitted by a light source have on an object? What's the impact of that curve on an object? We talked about last week. Wherever there's a spike, what? Yes, that color is exaggerated. Wherever there's a spike, that color is enhanced. Wherever there's, well, I showed it to you as a tweener, or actually the color, what's it called? The light source tool this morning. Remember, somebody had a nice red color, and we did with a red light, an A source light, and just poof, really exaggerated, right? It accentuates. That's a good word. All right. Now, if I see any of these spikes, wherever there's a spike, this color is accentuated. Wherever there's a trough, this color is de-accentuated, isn't it? All right. So that's why you want to have as smooth a light source as possible. Okay. I asked you to tell me about 3 color appearance systems, and you've got the CMYK book, you got focal tone, you got true match, you got Pantone, etc. What should a solid layer of magenta ink do to the light it receives? What should magenta do? Okay, so what should I showed you this last week too. We were talking about the top line with the paper though. What should magenta do? Magenta should absorb all the green, which is this piece in here, right? You saw this morning with the spectrophotometer. All right, and it should reflect all of the blue and all of the red. And what is it doing? Is this showing you what I've already showed you today in this afternoon's lecture? Yeah, it reflects a whole bunch over here of the red. Red is very good, right? But the blue is just very deficient. Okay, so it should be a curve that goes like that, right? But instead, what do we get? We get missing blue. All right. Which type of light source has the smoothest curve? And what is it? That's the tungsten lighting. That's fire. Okay. And that has a very high color rendering index. I think some of these. Okay. Which number is that? Okay. Well, good. I'm glad you brought it up. So if I have a sheet of white paper and it's in D50 lighting, red, green, and blue are striking it, what should this piece of paper do? Reflect all the red, all the green, all the blue. But, well, I showed you just a minute ago, the reflection of the light of paper, what does it do? I mean, instead of reflecting all of the red, the green, and the blue, it reflects most of the red, most of the green, but not enough blue. All right, that's what I'm getting at. Everything comes back around and around and around to this thing, is that we're missing blue. LAB is device independent, isn't it? LAB doesn't matter what device you use because it is. Okay? And RGB is dependent, isn't it? It's dependent upon the setting of the monitor, the brand of the monitor, the color of the phosphors, or the color of the LEDs, etc. Right? It's always dependent. True match inks are true match colors are supposed to be printed with CMYK. Yes. The CIE chromaticity diagram, which is called LAB, is based upon the visual perception of a white English male. True or false? And Hispanic female. The average French observer. The average human observer. The average human observer. Okay. That's important that you understand that the system has been brought into everybody. Okay. Okay. Pantone colors are designed to be simulated using CMYK. Yes or no? No. They're designed to be printed with spot inks, which returns profit to Pantone. All right. Good. Have a good day. You know, I come in, I was tired this morning, but this is so much fun. This class is more fun than, certainly more fun than estimating. I'm exhausted by the time I get through estimating. But this is fun. All right, have a good weekend, peoples. Don't forget you have a quiz due at 7 o'clock Sunday morning because I will start grading right after breakfast. I gotta get that, find that image and put it on here. Okay, computer. How come I couldn't find that? This is mine.